Good day, everyone. Today we're going to start our lecture video on Unit 3-1, and that is Regression Analysis. In the previous lectures, we talked about how regression analysis can be used to represent experiment results through an empirical model. And we do this to facilitate understanding, interpretation, and implementation of designed experiments. Now, regression analysis is actually most frequently used for unplanned experiments. So these are experiments from observation of uncontrolled phenomena or from historical records. Now, as I mentioned, we've talked about regression analysis and how it interplays closely with designed experiments. And now we're going to talk more about the fundamentals of regression analysis. And as I said, we're going to talk about model fitting, model adequacy checking, as well as, of course, hypothesis testing and creation of confidence intervals for the parameters of a regression model. Okay, but before we go into the details, okay, let's first talk about some basic terms. Okay, so now in regression analysis, we would like to see how a dependent or response variable y, relates to what we call the independent or predictor or regressor variables x sub I. Okay? So the regression model mathematically expresses the relationship between your response variable or your dependent variable y and your independent variables x sub i's from I equals 1 to k. Now in this course, we're going to focus on linear regression models. And what you can see here is an equation expressing a multiple linear regression model. Okay, so a multiple linear regression model would be expressed as such: y equals beta naught plus beta 1 x1 plus beta 2 x2 up to beta k x sub k plus the error term epsilon. Okay, and this is very familiar to you because we've used this several times already in the previous sessions. Okay, now why do we call this a multiple linear regression model? Okay, so let's look at the first term, multiple. It's multiple because we have several, more than one regressor variable. Okay, if there was just one regressor variable, this would be called a simple linear regression model. Now let's look at the term linear. Why is this called a linear model? Well, it's basically because in this equation, you can see that it is a linear function of the unknown parameters beta naught, beta 1, beta 2 to beta sub k. Okay, so regardless of the shape of the response surface that this model generates, as long as your parameters betas are linear, then this is considered a linear regression model. Now, since we have more than one regressor variable, then we call it a multiple linear regression model. Okay, now these betas actually are also called partial regression coefficients. Okay, so your beta naught, beta 1 to beta sub k, are partial regression coefficients. Why are they sometimes called as such? Because beta sub j is the expected change in y. Okay, so beta sub j is the expected change in y per unit change in x sub j when other regressors x sub I, where I is not equal to j, are held constant. So for example, beta 1 here is the expected change in y per unit change in x sub 1 when x sub 2 to x sub k are held constant. Okay. But in general, these betas are called regression coefficients. So beta I, for I equals 0 to k, are called regression coefficients. Okay, Now, you can see here a slightly different equation. As you can see, we've encountered this regression equation before in one of our factorial design examples, where this term here represents the interaction between say factor A and factor B, right? Now this, you can re-express this, okay, where you let x3 equals x1, x2, okay, and b3 be equal to b12, okay, beta 3 be equal to beta 1, 2, such that you would have this new expression y equals beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus epsilon. Okay, and this would still be a multiple linear regression model. Okay, you can also still express this kind of equation as a multiple linear regression model, okay, by letting x3 be equal to x1 squared, x4 be equal to x2 squared, x5 be equal to x1, x2, and then beta 3 be equal to beta 1, 1, beta 4 be equal to beta 2, 2, and beta 5 be equal to beta 1, 2. Okay, and so you would have this multiple linear regression model. So as long as your parameters, okay, your betas are linear, then you can consider this model as a multiple linear regression model. Okay. So as I mentioned, we're going to talk about model fitting. Okay, so model fitting is when we try to estimate the model parameters betas, okay, in the regression model. So suppose you have the true functional relationship y equals phi of x1 to x sub k, and this functional relationship is often unknown. So the goal is basically to approximate phi such that, okay, so the goal is basically to find those parameters such that we approximate phi. Okay, so how do we estimate the model parameters? So this is how you can express the data for multiple regression. So in multiple linear regression, you would have n be greater than k. Okay, so number of observations would be greater than k. And you would have an observed response y sub I for I equals 1 to n. Okay, so you have here your dependent variable y, okay, and you would have observations n observations for your dependent variable. Now for each instance, okay, of observed response for your dependent variable, you would also have a corresponding observed value or level of the regressor variable. So here you have x1 to x sub k. Okay, so that would be your data for multiple regression. And now we first talk about the assumptions about the multiple regression, linear regression model. No? So this is the familiar form in which your multiple linear regression model would come in. Okay, so and you can re-express it as such. Okay, and these are the main assumptions: that the expected value of your error, okay, is equal to 0. The variance of the error is equal to sigma squared, and the set epsilon I are uncorrelated random variables. So your error should not be correlated. Okay, and the most widely used method for estimating the regression coefficients, okay, one of the most widely used, okay, is the method of least squares. Okay, so this is the method of least squares, okay, is typically used for estimating the regression coefficients betas. Okay, so what you basically do here is you choose the beta such that the sum of the squares of the errors epsilon I is minimized. Now, in the method of least squares, what we basically want to do is to minimize this function here, okay, with respect to the beta. So we let L be equal to the summation of the square of the errors, okay, and E sub I here is just equal to Y sub I minus beta naught minus the summation of beta sub j x sub I j from j equals 1 to k. and that is from here. To minimize L with respect to betas, we should get the estimates beta naught hot, beta 1 hot to beta k sub hot, okay, that satisfies the following conditions. So we basically get the derivative of L with respect to beta naught and with respect to the beta sub j's for all j equals 1 to k. All right, and equate those to 0. Okay. So from here, okay, and getting the derivative, we would get this, okay, with respect to beta naught, and this with respect to the beta sub j's, okay, and equate that to 0. Now, simplifying those, then we would derive the least square normal equations as shown here. And the solution to these normal equations are your regression coefficient estimates, okay, which are beta naught hot, beta 1 hot, to beta k hot. These are also called your model parameters. Okay, now we can express this in vector form. Okay, so y equals x beta plus epsilon, where y here is the vector, okay, n by 1 vector of your observations for your dependent variable. X here is the n by p matrix of the levels of the independent variables. Okay, beta here is equal to your p by 1 vector of regression coefficients. Okay, so notice here that we have 1, okay, in the first column of the matrix. Okay, so p is k plus 1. Okay, going back, so epsilon here is your n by 1 vector of random variables, of random errors, I should say. All right, so then going back to the method of least squares, L would just be equal to the summation of the squares of your errors, and in vector form, this could be expressed as the transpose of the error vector multiplied by its by the error vector, okay, and replacing epsilon, okay, and using this, manipulating this equation, then we can just substitute y minus x beta for our error matrix, okay. So this would just be equal to this one. Okay, and using matrix operations, then L would just be equal to y prime, y minus beta prime x prime y, okay, minus y prime x beta plus beta prime x beta. Okay, and this would simplify to y prime y, okay, to beta prime x prime y. Why did that happen? Because this is basically scalar, okay? So this is also equal to this one. That's why we have minus 2 beta prime x prime y plus beta prime x beta. Okay, now what we want to do is to find the vector beta hat such that L is minimized. So we get a derivative of L with respect to the beta, okay? And this would just be equal to, so we get the derivative of this with respect to beta. Okay, so that would be negative 2x prime y plus 2x prime x beta hat. Okay. And manipulating this, okay, so this should be equal to 0. Manipulating that, you would have x prime x beta hat equals x prime y. Therefore, beta hat is equal to x prime x, okay, and the inverse of x prime x, okay, times x prime y. So you get the inverse of this, okay, multiply it on this side, you get this one times this expression here. Or this is actually your least square normal equations as well. Okay, and as you will notice, if you perform the operations here, you will still get the same equations as we got through the scalar form that we did a few slides back. Okay, so the fitted regression model in matrix form would be y hat equals x beta hat, okay, and the residuals, okay, the vector of residuals is just equal to y, okay, the actual observation minus the y hat, okay, which is the vector of predicted values. Okay, in scalar form, that would be y hat I is equal to beta not hat plus the summation of beta j hat x sub ij from j equals 1 to k for all I equals 1 to n. Okay, now we also have to estimate the variance sometimes. So the sum of square of error is just equal to this familiar equation here, the summation of the quantity y sub I minus yi hat squared, okay? And this is equal to summation of ei squared, okay? And in vector form, this would be e prime e. And we know that e is equal to y minus y hat, okay? And this is just equal to y minus, okay, x beta hat, okay, because this one is equal to this one, okay. So SSE is basically equal to, okay, so we just substitute this to the e's here, okay, this expression here. And so we perform the operations and we would get this equation. Now we remember that x prime x beta hat, okay, is also equal to x prime y, okay, because this one is equal to y. Therefore, this simplifies to SSE equals y prime y minus beta prime x prime y, beta hat prime x prime y. And this is actually the equation for the error or residual sum of squares, okay, with n minus p degrees of freedom. Okay, now based on that, okay, if you get the expected value of SSE, this is equal to sigma squared times n minus p. And therefore, the estimate of the variance, okay, sigma hat squared is equal to SSE over n minus p. Here are some properties of the estimators. So the beta hats are unbiased estimators of beta, and we can show it here, no? So the expected value of beta hat should be equal to beta, okay? So the true value of the parameter. Okay, so we know that beta hat is equal to x prime, the inverse of x prime x, okay, times x prime y, all right? And we can substitute x beta plus epsilon to y here, okay? So we have this expression. Now, if we expand that further, we would have x prime, the inverse of x prime x times x prime x plus beta, okay, plus the inverse of x prime x times x prime minus epsilon, times epsilon, I should say. Now, we know that this one here, okay, is just, oops. Now, we know that this one here is just equal to I, or the identity matrix. So this would just be equal to beta. And then we know that the expected value of error is 0, okay? Therefore, this would just cancel out to 0, and what you are left with is expected value of beta, okay? And you would then have beta, all right? So expected value of beta hat is equal to beta, which means that the beta hats are unbiased estimators of beta. Okay, furthermore on properties of the estimator, so let's look at the covariance of the estimated parameters beta hat, okay? This is equal to the expected value, okay, of the quantity beta hat minus the expected value of beta hat, okay, times the quantity beta hat minus expected value of beta hat transpose, okay, so prime, no? And that would just be equal to sigma squared times the inverse of x prime x. Okay, now in this matrix, the ith main diagonal element, okay, is actually the variance of the individual estimated regression coefficient, also called the model parameters. Okay, so again, the ith main diagonal element, okay, in this is the variance of the individual estimated regression coefficient. Now, the ijth element are the covariances between beta I hat and beta j hat. Okay. Furthermore, the square root of the main diagonal elements are the standard errors of the model parameters. So now let's look at an example of several examples on model fitting. Okay, so let's first look at the viscosity of a polymer example on model fitting. Okay, so suppose you have 16 observations on the viscosity of a polymer Y, okay, and two process variables, reaction temperature x sub 1 and catalyst feed rate x sub 2. So viscosity of a polymer here is the dependent variable, okay, Y, and reaction temperature and catalyst feed rate here, denoted as x1 and x2, are your independent variable, otherwise known as your regressor variables or your predictor variables. Okay, so our task here is to find the fitted multiple regression model to the data, okay, to the 16 observations, and this would be the fitted multiple regression model. Okay, so suppose that this is the viscosity data. This example is from Design and Analysis by Montgomery. Okay, so you have 16 observations, you have temperature and catalyst feed rate, okay, values corresponding to each observed viscosity. Okay, and the viscosity is in centistocks at 100 degrees Celsius. All right, so 12. Now, our task is to fit a regression model given this data. Or our task is to fit a regression model to this data. Okay, now we can express the given data in matrix form. So our x's would be the levels of our regressor variables, and of course we have 1 in the first column, and then the levels of our regressor variables in the succeeding columns. This would be temperature and okay, so we have 1 in the first column, and then these are the temperature values, and these are your catalyst feed. And then we have here another matrix Y, which is basically the observed values for the response variable viscosity. Okay, so we need the X to solve for the beta hat matrix. Okay, we need first to get X prime X matrix, so X transpose times X. Okay, so that would just be equal to this. All right, and if we perform the operations, we would get this matrix. So note, okay, that X is a 16, okay, 16 by P, where P is equal to K plus 1. So 16 by 3 matrix, while Y is a 16 by 1 matrix. Okay, therefore, X prime X is equal to a 3 by 3 matrix, because this one is 3 by 16, 16 by 3, so you would have 3 by 3 matrix. Okay, and we also need the X prime Y vector. Okay, X prime Y vector. So the X prime Y vector is just equal to this, okay? And doing matrix multiplication, we would get this 3 by 1 matrix, because we have a 3 by 16 multiplied by a 16 by 1. So we have a 3 by 1 matrix here, okay? Now we know that beta hat is just equal to the inverse of X prime X times X prime Y, okay? So first, we got the inverse of this matrix and multiply it by this matrix here, okay, to get this matrix, okay. Therefore, our fitted regression model is y hat equals 1566.08, that's our beta naught, plus 7.62 x1, so 7.62 is beta 1 hat, okay, plus 8.58 x2. 8.58 is beta 2 hat, okay. Now, of course, we have to do model adequacy checking, okay. So, again, we have 16 observations, okay. Using our fitted model, we can derive the predicted value yi hat, okay, and then we can compute for the residual values. E1, okay, E1 is equal to yi minus y hat I, okay. Therefore, we would have these values, 16 residuals, and we could construct a normal percent probability for these residual values, and we can see this, okay. So far, it looks satisfactory. However, if we plot, okay, the residual value, okay, residual values versus the predicted viscosity in centric stokes, we can see that there is a pattern, no? The residuals are fanning out, which indicates that the variability actually increases with increasing value of the viscosity, okay. Now, if we plot the residuals versus the regressor values, okay, for temperature and catalyst feed rate, we can see that residual also increases as the temperature increases, okay. Okay, so let's look at another example. Okay, so this time we're going to fit the model, okay, to a 2 to the 3 factorial design experiment. Okay, so this is again from Montgomery. A chemical engineer is investigating the yield of a process. Okay, so 3 process variables are of interest: temperature, pressure, and catalyst concentration. Each variable can be run at a low and a high level, and the engineer decides to run a 2 to the 3 design with 4 center points. The design and the resulting yields are shown in figure 10.5 of the book, okay, where we have shown both the natural levels of the design factor and the +1 and -1 coded variable notation normally employed in 2 to the k factorial designs to represent the factor levels. Now, suppose that the engineer decides to fit a main effects only model, say y equals beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus epsilon. So the interactions are left out in this regression model. So let's see. So these are the given data, okay? Okay, and this is also represented in this cube here. So as you can see, we have here the process variables, temperature, pressure, and concentration. And these are the observed values for the 12 runs, okay? And then we have the coded variables here, okay? And these are the relationship between the coded and the normal values of the variables. And these are the values for your response variable, y, which is yield. Okay, so again, we can express in terms of matrix form. Our X matrix is equal to this. So you have 1 in the first column, and this would be the value of the coded values of the variables for temperature, pressure, and concentration, respectively. And then these are the observed values for yield. Okay, so again, we have to get x prime x and then x prime y. Okay, so this is our x prime x and this is our x prime y. Now, you can see here that this is a diagonal matrix, and this indicates that the design is orthogonal. Okay, therefore, our beta hat is just again equal to the inverse of this matrix times x prime y. okay? And multiplying these two matrices, we get the values for the model parameter estimates, okay? Therefore, our fitted regression model is 1 y hat equals 51 plus 5.625 plus 10.625 plus 1.125 x3. Okay, so based on this model, again, let's recall that these are also called partial regression coefficients, because this would be interpreted as so 5.625 here, okay, is interpreted as the expected change in y with a corresponding unit change in x1, holding x2 and x3 constant. Okay. Now, recall in factorial design, you can also estimate the effects. Okay, so for temperature here, the effect estimate for temperature is just equal to the average at a high level of temperature minus the average at low level of temperature, and that would be equal to 56.75 minus 45.5, and this is equal to 11.25. Now recall that when we were doing this, to get the regression coefficient, we divide this by 2 because we have coded variables from -1 to 1, right? So, and 11.25 here divided by 2 is just equal to 5.625. Okay, and this example also illustrates that the effect estimates from a 2 to the k design, okay, from 2 to the k designs are least squares estimates. Okay, now let's move on to another example. Okay, so let's try to perform model fitting for a 2 to the 3 factorial design with a missing observation. So this is where we can illustrate how regression analysis can actually be used in experiments where something has gone wrong, no? So designed experiments where something has gone wrong. So let's look at this, also from Montgomery. Consider the 2 to the 3 factorial design with 4 center points from example 10.2. Suppose that, so from the previous example, suppose that when this experiment was performed, the run with all variables at the high level, okay, was missing. So that would be the 8th run in the previous example. This can happen for a variety of reasons. Okay, so again, so say that this run here, okay, this run where all variables are at high, okay, is missing. Okay. Now this can happen for a variety of reasons. This could include the measurement system producing a faulty reading, okay. The combination of factory levels may prove infeasible, or the experimental unit may be damaged, and so on, no? Okay, so say that we want to fit the main effects model, y equals beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus epsilon, okay, using the 11 remaining observations. Okay, so again, we express the data in matrix form. So x is equal to this, all right? So we only have a 4 by 11 matrix here instead of the 4 by 12 matrix, okay? And here we have an 11 by 1 matrix. Okay. Now, similarly, we get x prime x and then x prime y. Okay, and this would be the corresponding matrices. Now, x prime x here and consequently the inverse of x prime x are no longer diagonal, as you can see, no? Therefore, the design is no longer orthogonal due to the missing observation. And you will also observe that the variances are now larger. Okay, now, anyway, let's proceed to estimating the model parameters, beta hat. And this is equal to, again, this expression here, using what we got for the these matrices. We would have this 4 by 1 matrix for beta hat. Therefore, the fitted model is 51.25 plus 5.75 x1 plus 10.75 x2 plus 1.25 x3. It's not so different from the previous fitted model. Okay, how about if we have inaccurate design levels, no? Let's try to look at an example where we want to fit a regression model, okay, to a factorial design where the design levels are inaccurate. Okay. So again, from Montgomery, when running a designed experiment, it is sometimes difficult to reach and hold the precise factor levels required by the design. Now, small discrepancies are not important, but large ones are potentially of more concern. Regression methods are useful in the analysis of design experiment where the experimenter has been unable to obtain the required factor levels. Okay, so this can be really useful, no, in real life, no, when you're performing your experiments and you cannot be, very accurate with the levels of your factor levels. So regression analysis can come in handy. So to illustrate the usefulness of regression analysis, okay, let's try to modify a little bit our previous example, okay, to show one where the design levels are inaccurate, meaning the experimenter was not able to uphold, okay, the actual required factor levels, okay. So say that these are the actual temperature and pressure temperature, pressure, and concentration values, okay, in the experiment, okay. Now, given the required levels, okay, and the relationship between the normal value and the coded variable, okay, this can be translated in terms of the coded variables as such, okay, and say that these are your observed values for your dependent variable. Okay, now what we want to do again is basically to fit the main effects model, okay. So given these values, okay, we just go through the same process. We have the X matrix, the Y matrix, and we get the X prime X matrix and the X prime Y matrix to be able to estimate the model parameters. Okay, and this would be our fitted model. Comparing it with the original model, since the deviations are not that big, okay, the resulting fitted model is also not very different from the original one. Okay, as you can see here, okay, the deviations are not so big. Now we move on to hypothesis testing in multiple regression.